Hello, my name is Brandon Chen, and today I will be describing the motion of the helicopter on Mars for Physics 211 Project 1. From the velocity and position equations given in the solution video, I was able to graph the horizontal and vertical motion of the helicopter from these two equations. Using big T as 10 seconds, alpha as 10, and beta as 1, we can see the helicopter starts at T is equal to negative big T, or negative 10 seconds, and ends its motion at T is equal to big T, or 10 seconds. As you can see, this is true for both the velocity and position graphs of the helicopter. Now, let's analyze these two graphs. Looking at the graph for the helicopter's velocity, we can see the equations for the horizontal and vertical velocity are in the table to the left of the graph. Looking at this table, we can see the red line represents the horizontal velocity, while the blue line represents the vertical velocity of the helicopter. Analyzing the horizontal velocity of the helicopter, we can see that at the beginning of its motion, the horizontal velocity increases until it reaches its max velocity at t is equal to 0, before decreasing again until its velocity reaches 0 at the end of its motion. For the vertical velocity, we can see that the velocity increases for a couple of seconds, then decreases again, reaching velocity is equal to 0 for a couple of seconds, increases again and decreases again with this velocity equal to 0 at the end of its motion. Looking at the graph for the helicopter's position, we can see the equations for the horizontal and vertical position are again the same colors, with the red being the horizontal and the blue being the vertical. Analyzing the position graph of the helicopter, we can see the horizontal position is an almost linear line upwards, with the helicopter's velocity slightly increasing or curving upwards after it begins and slightly decreasing or curving downwards towards the end of its motion. Looking at the vertical position graph, we can see that from the start of its motion to t is equal to 0, the helicopter's altitude increases, but slows down and hovers at the same altitude for a couple of seconds. After these couple of seconds, the helicopter soon starts rising again before stopping at the end of its motion. All of this lines up with the velocity graphs we saw before. So what would the motion diagram of the helicopter look like knowing all of this data? Making a motion diagram from the data of these graphs, we can see the diagram looks similar to the Y position graph. As you can see, at the beginning of the flight, the helicopter starts out slow, but soon increases in velocity. However, while continuing to move horizontally, the helicopter seems to hover at the same altitude. After a couple of seconds, the helicopter again starts to increase in vertical velocity and gains more altitude. However, as it approaches t is equal to big T, or at the end of its motion, the helicopter slows down. Thank you for watching the motion description of the helicopter on Mars project. Now, Paolo, my fellow group mate for this project, will explain what all of this data means and make sense of the situation.
Hi, my name is Paolo, and I'll be taking over for the sense-making part of this project. To start us off, the information we're given is limited to the acceleration equation with a few defined variables, the known constants alpha and beta, and then we have the unknown information, the time constant t, and the horizontal distance away d from initial to the final. Finding d, or the horizontal distance, is one objective of finding the solution to the given problem regarding distance. So, the tasks we're given are to be able to describe the motion of the helicopter, how much time it takes or how much time the helicopter spends in the air, and where the helicopter lands. Now, to find those things, we need to know the velocity and position equations of this given situation, found by integrating. You integrate acceleration to get velocity, and you integrate velocity to get position. The two equations here show the end result of that. So now, we can use the distance equation to find delta x and delta y with the differing parts of the equation, which is the change in x and the change in y. This right here will be the change in x, and this over here will be the change in y. So, the initial time is negative t, and the final time is positive t. We can then proceed to plug in those values in the equation for the x, and then we can get d, which is 2 beta time squared over 3. Delta x gives you the answer for d, which is the horizontal change for motion. And so delta y is given through the same process over here. And now we find t, or rather t squared. Here in this equation, we change the variables around and solve algebraically for t squared. So t squared, when you swap these around, you get t squared equals 3d over 2 beta. And so you can plug that in for the delta y, and you can get the true value of delta y down here, which is alpha over 35 beta times d. So now we have now obtained how far away it is from the initial rover, now that we have both the change in x and the change in y that the helicopter lands. And now we also know how much time it spends in the air after we solve for t up here, simply by taking the square root of t squared. Now we still have yet to describe the motion of the helicopter, and to do that we need to make certain graphs to represent the situation. In the velocity graph here, you can see the different x and the y. By doing this, by separating these equations, you can identify more clearly how it moves along these axes. So, after evaluating from there, by changing alpha or beta in this graph, the velocity and acceleration decreases until the lines are inverted after becoming a straight line on the x-axis at value 0. Multiplying by a constant of 0 equates to 0, and negative alpha or beta suggests that the helicopter's direction has changed, not the magnitude. Much the same goes for the position graph, except instead of the velocity, it represents the location of the helicopter at a given time. In both cases, decreasing t will shrink the graph, as shown here, and while it does keep the same general motion, it is on a much smaller scale because of the lesser air time. Thank you for your time. I now pass the evaluation of this problem in regards to prior course content to my group member, Ashur.
Hello, my name is Ashur. For this section, we will be analyzing how this project's problem compares to other problems we have done in this Physics 211 course. First, let's assess what we know about this problem. For this project, we first need to describe the motion of the helicopter. We are tasked with finding how long the helicopter was in the air for, as well as where the helicopter lands after being in the air. I would also like to note that this problem is on Mars compared to these two problems I will be discussing, which are on Earth. Thus, the gravity will be different. The Mars gravity is negative 3.27 meters per second squared, where Earth is 9.78 meters per second squared. For this first comparison, we picked Super Mario's acceleration. This can be found on the slides for lecture 4. This Mario problem worked in 2 dimensions. The problem asked us to find how long it takes for Mario to return to his initial velocity and what position Mario is at this time. This is similar to the problem we are facing now with the helicopter. However, instead of working in 2 dimensions, this problem with the helicopter requires that we work in 3. For both of these problems, we can see that the acceleration is not constant throughout the motion. If each was consistent, their acceleration graph would present as a horizontal line when put on a velocity versus time graph. For this final problem, we picked activity 1 for homework 3, week 3, about throwing a ball on top of a cliff. From the bottom, we are asked to find how high the cliff is. In other words, it's asking for the final position of the object in terms of height. This is different from the problem we are facing with respect to what we are solving for. Instead of finding only the position of the helicopter, we are also tasked with finding how long the helicopter is spent in the air when it returns to its initial velocity. And that concludes our video. Thank you for your time.